This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com.
Hello, this is the lecture on electromagnetism for Ph.D. entrance exams, and this is the third part. I am Devashish Sanya from the Department of Physics. We will go to the first problem. So this is the first problem. Consider a tiny current loop driven by a sinusoidal alternating current. If the surface integral of its time average pointing vector is constant, then show that the magnitude of the time average magnetic field intensity at any arbitrary position r is proportional to 1 by r. So this is actually an oscillating magnetic dipole. So we have to find out the magnetic field due to magnetic field and electric field due to an oscillating magnetic dipole. We will not do all these things, so we will do it later. So we will do it very fast. So what is the time average pointing vector? So what we have asked is time average magnetic field intensity at any arbitrary position is proportional to r. The surface integral of its time average pointing vector is constant. So this is my time average pointing vector, and this is over a surface of a sphere of radius r. So r is a constant. So what we are telling is this is independent of r. So this is independent of r, that means P average, time average, this is also should be 1 by r square. Then only this r square and r square will cancel, and this entire thing will be independent of r. So if this is independent, this goes as 1 by this goes as 1 by r square, then what happens? That means P goes as time average T goes as 1 by r, and time average T goes as 1 by r. Right? So this is simple, but if we do it in details later. We go to the next problem. Consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius a and carries a charge plus q. The outer shell has a radius b and carries a charge minus q. The empty space between them is half filled by a hemispherical shell of a dielectric having permittivity epsilon 1. And the remaining space between the shells is filled with air having permittivity epsilon naught. Show that the electric field between the space, that is where r lies between a and b, is given by this is q by 2 pi epsilon naught by epsilon 1 by r square into r cap. So this is the figure. This is the dielectric, the inner shell, the inner radius is a and the outer radius is b. The inside we have a hemispherical dielectric with this is the permittivity epsilon 1, and this region has permittivity epsilon naught. This is air. This thing has charge minus q. So what we have to find out? The electric field in this region. Now so what we have to know is that the electric field, we know, so electric field from the figure we can make out, the electric field will be radially outwards. And it will be radially outwards. At the same time, we know that the electric field in this case will be continuous across the interface. The tangent component of the electric field is continuous across the interface. So the electric field here and the electric field here, just across the boundary, will be the same. And from the symmetry of the problem, you can say that the electric field will be same everywhere. And it is continuous across this and is continuous across this. So what we can write? So E1 is equal to E2 is equal to E. So in this region, E is same everywhere and it is E. But the displacement vector d1 is epsilon 1e and d2 is epsilon into E. Yeah? And then we use Gauss's law. Gauss's law, so we will use Gauss's law expressed in terms of displacement vector. So we will take a Gaussian surface, spherical one, and then we use Gauss's law. Right? So d1 2 pi r square plus d2 2 pi r square. So this is d1. This is the d1 across half of the surface. This is the d2 across half of the surface. This is the area of the half of the surface. This is the area of half of the surface, and that is equal to q. This is the enclosed charge. That's it. And from there, use these relations. D1, write D1 in terms of E and D2 in terms of E, and you will get the desired expression. Do the next problem. To identify small electric dipoles with an equilibrium separation R, which is assumed to be a constant. Each dipole has charges plus minus q of mass m, separated by R. Each dipole can execute simple harmonic motion in angular frequency omega. Recall that the electric field across the axis of a dipole at distance very far off R is given by 1 by 4 pi epsilon naught P modulus. So this is, we are just talking about this magnitude of the electric field. This is the dipole moment by R2. So the electric field along the axis of a dipole at a distance very far off R is given by this. It is the dipole. Show that the angular frequency of oscillation of the dipole is omega square plus 2 omega square. So what is this omega square? This is the natural frequency. We'll see what is natural frequency here, and what is capital omega. Capital omega square is 1 by 4 pi epsilon naught q square divided by m r2. So this is a picture. So we have two dipoles. This one dipole, this one dipole, and they are separated by a large distance r. So suppose this dipole. So what is the electric field due to this dipole here? That is given. And this is the dipole moment. So this is the electric field due to this dipole at this position. And remember, this R is much greater than R. So that's why these two these two act like dipoles. Now, what is a dipole? Dipole means there is an electric field somewhere. There is an internal electric field, and because of the electric field, there is a charge separation between plus and minus. Right? So the dipole is due to an electric field. And when such a dipole is, so this is the electric field, and because of the electric field, there is charge separation and we have a dipole. Now if in this electric field the dipole is slightly rotated like this, then it's going to have angular oscillations. And the frequency of that oscillation in this problem is omega. Okay, this is the natural frequency. And this natural frequency can easily be found out. So this is, and now what's happening? So this is the natural, the angular frequency of small oscillation of dipole P, and the electric field E is given by PE by R. So this is a normal, this is a simple problem here, this one. So if there is an electric field E, then if you rotate the dipole by a small angle theta, then what is the torque acting on it? P cross C. And torque is nothing but is equal to I is the moment of inertia, d2 theta dt square. So from here, if theta is small, you can easily conclude that this is the equation of a simple harmonic motion. And from here you can easily calculate that the frequency of oscillation will be Pe by R. Now in this case the electric field E is due to two. This can be broken up into two electric fields. One is E0, one is the natural frequency, natural electric field which is causing the dipole, say, and another is the electric field due to the other dipole which is very far off, and this is actually a very weak field because of this dipole. That's it. So you just have to substitute this thing here. And remember what is omega square? Omega square is E0 P by I. Okay, so so this is omega square. And what is P? P is equal to QR. Remember this? And what is moment of inertia in this problem? It is m small m into r by 2 whole square plus m r by 2 whole square, because the two masses. This is m, this is m, and the separation from the center is r by 2. So it will oscillate about the center. So it's r by 2. That's it. Just so E dipole we know. That's it. You just substitute whatever the values I have given you, and you get the result. So this a problem is the vector potential for an almost point-like magnetic dipole located at the origin is A is equal to mu sin theta 4 pi r square phi cap, expressed in spherical polar coordinates. A particle of mass m charged tube moving in an equatorial plane of the dipole starts at time t is equal to 0 with an initial speed v0 and impact parameter v. So we have to find out what is this instantaneous speed at the point of closest approach. So they have given these four options. Remember, this is a magnetic dipole. So what you have only is magnetic field. There is no electric field, there is only magnetic field. Magnetic field you can find out by taking the curl of this. And we know that magnetic field does not do any work. So that means it cannot change the energy of the particle. So you can easily make out what will be the answer. I don't have to tell you, because the magnetic field does not do any work. We go to the next problem. A laser beam propagates from fiber 1 to fiber 2 in a cavity made up of two optical fibers. The loss factor of fiber 2 is 10 dB per kilometer. dB is decibel per kilometer. If E to D denotes the electric field in fiber 2 at a distance d from the interface, the ratio E to 0 by E to D is equal to 10 to the power 5. For d is equal to 10 kilometers. This we have to show. Right? So E to D is defined. So we have to show that the ratio E to 0 by E to D is in 10 to the power 5 when d is equal to 10 kilometers. So this is the fiber 1, fiber 2. So what's happening as the wave is propagating? There is attenuation, so this loss of energy. So when it goes a distance d, the intensity has already decreased, and this is given. The loss factor is given in decibel per kilometer. So what is this? So this is a starting point. So the intensity at a distance d is this, and distance and intensity, I say the reference point is this, and that is defined by Pd is equal to P0 e to the power minus alpha d, where alpha is this constant, is the what is called loss factor. But this is a loss factor, so from this relation you can easily find out what is alpha. Alpha is equal to minus 1 by d ln this, then Pd divided by P0. Pd and P0 are the intensities. Right. So now this is loss factor, but there they have given, so here it is, the dimension is 1 by distance, but there they have given in terms of decibel per kilometer. So this, you can define another loss factor, which is alpha decibel, which is given by this, minus 10 by d log Pd by Pc. This minus 10 by d log, see log is to the base 10, so minus t log Pd by P0 is the decibel unit. Okay, so that is the decibel unit. So instead of working with this expression, generally we work with this expression. So this is given, and Pd you know will be E squared d, and P0 will be E squared 0. Here we find out the ratio. That's not difficult. So this part minus t log Pd by P0 is the decibel unit, and that's why it is decibel per kilometer. That's how decibel is defined. We go to the next problem. A perfectly conducting fluid of permittivity epsilon and permeability mu flows with a uniform velocity v in the presence of a time-dependent electric field D and magnetic field B. If there is a finite current density J, then show that curl of V is del B del T. So here, with perfectly conducting means sigma is the conductivity is infinite. And we know this relation, J is equal to sigma E plus V cross B. Is it not? The current density is equal to sigma E. So this is due to electric field, and this is due to the magnetic field. Right. And this is Maxwell's equation. Curl of E is equal to minus del B del T. Now here it is given J is finite. So J is finite, but sigma is infinity. If sigma is infinity, then this can be finite only when this quantity tends to 0. Hence, we can write E is equal to minus V cross B. And after that, it's very trivial to show that from here you get this. We go to the next problem. A small circular wire loop of radius A and number of turns n is oriented with its axis parallel to the direction of the local magnetic field B. A resistors R and galvanometer are connected to the coil. The coil is now flipped so that its axis is now reversed. The galvanometer measures the total current Q that flows through it. Show that the expression for Q is this. So this is the figure. So this is, say, the initial configuration, and after that suddenly it is turned by 180 degree. And when it is turned by 180 degree, current or charge flows through this coil. And they are given that the charge is Q. So we have to find out that the amount of charge that has flown through the circuit is this much. So this is not difficult. So we have to find the induced voltage. Induced voltage is del phi del T, change in flux, and the flux change is taken place in say time delta t, then is delta phi by delta t, and voltage is equal to current into R. So if a charge Q has flowed in time delta t, then the current is Q by delta t. That's it. So from there you can calculate delta phi very easily. In one case, your phi is perpendicular, your normal to the surface is aligned parallel, is aligned in the direction of the magnetic field, and when you say flip it, then the normal to the surface is aligned opposite to the magnetic field. So we know the expression for flux, B magnetic field dot N ds. N is the unit normal to the surface. So from this you can just do it quite easily. So I won't dwell on this problem anymore. So we go to this next problem. A long cylindrical wire of radius r and conductivity sigma lying across the z axis carries a uniform axial current I, axial current density I. Show that the pointing vector on the surface of the wire is this. This is what we have to show in cylindrical coordinates. So we are using cylindrical coordinates. So I is equal to sigma u. I is the current density. So I will be sigma u, and I total is what? I total is your I into cross section area. Okay, this is total current that is flowing, and if the total current is given, then what happens? You can find out the magnetic field due to this total current, which is mu 0 I total by 2 pi r, and you know the direction. I will not explain these things. So if a total current in the wire is given, then you know the direction of the B, and I total is also known from this expression. So S is 1 by mu naught E cross B. So find it out, show that the pointing vector. So E can be found out from here, and B can be found out from here, and E and B will be perpendicular to each other. So that's it. So you can find it, you can find S. Okay. We go to the next problem. The electric potential at the boundary of a spherical cavity of radius r as a function of polar angle theta is V0 cos square theta by 2. The charge density inside the cavity is 0 everywhere. Show that the potential at a distance r by 2 is half V0 1 plus half cos theta. So you have a cavities, you have a shell and you have a cavity surrounding the cavity, and the electric potential at the shell is given by this. So it depends, this is in spherical coordinates, so it depends only on theta, as you can see. So if this is given, so at a this is the distance r, so at a distance r by 2 you have to show this is the potential. So this is straightforward. So inside there is no charge, that means Cauchy equation will be satisfied. So potential will be del square V is equal to 0. And we know inside the cavity the potential will be of this form. Alm is some coefficient, r to the power L, P ml cos theta. This is associated Legendre polynomial, and this is e to the power m phi. Where we know that m goes from minus L to plus L, and L goes from 0, 1, 2, 3 like that. So if this is, so here you can see that if at this at distance r, this is the potential, then there can be contribution only from A00 and A10. All other coefficients will be 0. Because if you take so m will always be 0, because if we take m to be non-zero, then phi dependence will come, and if we take L greater than 1, then we will have other terms, other complicated terms, which will not satisfy this relation. So we will get contribution only from this term and this term. So you have to find out this term and this term. That you do. So that at r is equal to r, this is satisfied. And once you get this term and this term, it's trivial. You can find out what is the potential at r by 2. And you will get this is the potential. Once you find out this is also easy to find out. Now go to the next problem. The charge density and current of an infinitely long perfectly conducting wire of radius a, which lies along the z-axis, as measured by a static observer, are 0 and a constant r. The charge density measured by an observer who moves at a speed v is equal to beta c parallel to the wire along the direction of the current is this. So if the observer is static, so he is measuring that the current is r, but the charge density is 0 of the wire of radius a. Okay. So now another observer is there who is moving at the speed of v with respect to the first observer. So to that observer there will be a charge density. Okay. So we have to show that the charge density as observed by that observer is this. So this is actually a problem of two reference frames and how the electric and magnetic field change in the two reference frames. So this is a problem of special relativity. So suppose the frame S. So our problem is like this. So this is, so suppose I take my so the current is moving in this direction, and the second observer is also now moving in this direction. That is this is the y-axis and this is the z-axis. So how are the electric fields connected in the two reference frames? So the frame that is moving is S bar and the frame that is static is S. So Ex bar is equal to Ex, Ey bar is equal to gamma, Ey minus B, Bz, gamma, the usual notation in special STR, and Ez bar is equal to gamma, Ez plus B, By. Now, this is general. So, if we take okay, so if you take say a point, say at a distance r from the wire, then if you just consider the electric field, the wire is infinite, then it is, we are using Gauss's law. So E into 2, so we are considering a cylindrical Gaussian surface. So the total flux across the cylindrical Gaussian surface is 2 into 2 pi r. R is the distance of the Gaussian surface from the center of the wire into L. L is the length of the cylinder that we are considering. And that should be equal to the total charge that is enclosed by this Gaussian surface, which is pi a square is the cross section of the wire into L is the length. So this is the total volume. Total volume is multiplied by rho density. So this is the total charge and then divided by epsilon naught. Right? This is always true. And B is, if the current is I, then B is mu 0 I by 2 pi. Now in the first case where there is charge is 0, charge density, P is 0. Right? But this is B. This is the B. I have not written down the magnitude. I have not written down the direction. I have just written down the magnitude. You know the direction. If this is the direction of the current, then what will be the direction of the magnetic field? So in the first case, so we'll take a point in the upper xz plane. We'll use this. So we consider a point P which is in the xz plane. This is the xz plane. We consider a point, and we can find the answer. So in the xz plane, suppose this point is there. So Ez is 0. Right? Ez is 0. And what is By? We are going to use this one. Ez is 0. And what is By? So we know the magnitude. Find out the direction. The current is flowing in this direction. This is, say, point P in the zx plane. So what will be the direction of the magnetic field? The magnetic field will be directed opposite to y, and this magnitude will be this much. Is it not? So that will give me Ez. This is the electric field that we observe in the moving frame at this point. Right? This is what we observe. So we are using this relation. So we will just take a suitable point. You can choose other point also. It's up to you. I have taken a point in the zx plane. And at that point, I am going to find out Ez. Ez is 0. And what is By? What is the y component of the magnetic field? If I know this, I can find out what is Ez bar. What is the magnetic field in the, what is the electric field in the moving reference frame. And once I find this, I just put it here, substitute it here, and then I can find out what is the rho in the moving reference frame. So in the static reference frame, rho is 0, but in the moving reference frame, rho will not be 0. It will be a non-zero quantity. And we have to find out this is the non-zero quantity. So you can do it. Just use this expression. And then this. And we go to the last problem of today. An infinitely long solenoid of radius r0 centered at the origin produces a time-dependent magnetic field alpha divided by pi r0 square cos omega t is placed along the z-axis. The circular loop of radius r, which carries unit line charge density, is placed initially at rest on the xy plane with its center on the z-axis. If r is greater than r0, show that the magnitude of the angular momentum of the loop is this. So what is the problem? So this is my solenoid, this is the radius r0, and this is another loop of radius r, which is kept like this, and this is the z-axis. Now the magnetic field inside the solenoid is oscillating. That is what is given in the problem. Time-dependent magnetic field. So what is happening is that the magnetic flux across this loop is changing with time, and as a result there will be an electric field So that electric field, what it will do, is going to act on this loop, and this loop is charged. Since the loop is charged, what will happen? This electric field will rotate the loop, and as a result it will acquire an angular momentum. So what they have asked you to find out the angular momentum of the loop at any particular time. So now we know this. So first we have to use Faraday's law, or we use Maxwell's equation. This is the Maxwell's equation in integral form. So E into 2 pi r, that is curl of E is equal to minus del u del t. If you write it in integral form, it becomes E into 2 pi r is equal to minus ddt of the flux across the surface. So in our case, E is tangential to this. E is tangential to this circle, and the flux is the flux across this, because outside there is no flux. Whatever magnetic field is there is inside, so the flux is changing here. So whatever the flux is here, and we have to take a time derivative of this. So B is the magnetic field into pi r 0 square. So that is the total flux, and B is this one. This is B. This is given. So once we know this, so this is easy to calculate. You can find E. You can find the electric field that is acting here. Alright. E into 2 pi r is this. Now you have to calculate the angular momentum, that is, you have to calculate the torque. What is the torque? Torque is equal to R cross F, but this is a loop of radius R. So R, what is F here? So if you take infinitesimal length dl here, so what is the charge, total charge? Sigma into dl. Sigma is the line charge density, into dl is the total charge. So the total force that is acting on an infinitesimal length along the circumference is E sigma dl, right? So the total torque is R cross E sigma dl, and then we have to integrate this across this whole loop, and that is easy to do. You can easily see E and R are perpendicular to each other. So there is so this integration is easy. Magnitude of E is constant. So once you do this, you can easily find this integral. And what is sigma? Sigma is 1 by 2 pi r, because it is given that the loop carries 1 unit of charge, and so the line density will be 1 by 2 pi r. That's it. We do this integration, and then we substitute the value of E from here. Alright, and we'll get the torque. So you'll get the torque. So torque, whatever torque you get here, the torque is equal to I into d omega dt. Omega is the angular frequency of this. So this is now rotating. So capital omega is the angular frequency of this loop. So I d omega dt is the torque, and that is equal to whatever I get here by substituting the value of E here. That's it. So I can easily integrate for omega. I is the moment of inertia. So I can integrate for omega, and once I integrate for omega, I can find out the angular momentum. How? You know the angular momentum is L is equal to I into omega. Substitute this value of omega, and we are expected to get this answer. So that's how this problem is done. So we'll end here, and Next, in the meantime, I will do classical mechanics. I will explain some points in classical mechanics and electrodynamics. And also I will also start doing problems in quantum mechanics next time onwards. So thank you.